So you know how when objects interact, you can pretty well predict what the outcome's going to be? You can do this pretty simply, using what you already know from physics or just by using basic observation. For instance, if you drop a ball on the ground, depending on what it's made out of and what the ground is made out of, it's either going to stay on the ground or bounce back up and down. Likewise, if you shoot a paintball at a fairly close wall, depending on how good your aim is, it's going to hit where you aimed. That is, if we neglect all other outside forces such as wind and air drag. So life is good, and the universe makes perfect sense. Enjoy that feeling while it lasts. Introducing wave and particle duality. So, what are waves and particles, and what makes them different? Particles are thought of as very small objects which have physical characteristics such as mass and volume. For example, protons and electrons are particles. We can also say that baseballs or basketballs are particles. These are given physical characteristics such as mass and volume, so we can essentially say that they're the same thing. However, protons can be further subdivided into quarks, and you guessed it, quarks are particles too. But since quarks and electrons cannot be further subdivided, we refer to them as fundamental particles. Because of this, most particle theories and experiments are done with electrons. Now, what are waves? Waves are classified as oscillations accompanied by a transfer of energy. There are many things that we categorize as waves. We have waves on the water, vibrational waves, light waves, and more recently, gravitational waves. And this is nowhere near a complete list of everything we can classify as a wave. There are a multitude of things that exhibit wave-like behavior. Furthermore, waves can be categorized into two main types, mechanical and electromagnetic waves. Mechanical waves require a medium to propagate, such as when you whip a jump rope and watch a pulse travel through it. The rope is the medium. Electromagnetic waves are waves that do not require a medium to travel. Visible light, as well as most rays from the sun, gamma rays, X-rays, etc., are examples of electromagnetic waves. A neat characteristic of waves is that when they collide, they superimpose. This means that they can either add together or cancel each other out. This is typically not what we see happen when particles collide. Usually, when free particles collide, they bounce off of each other and go in different directions, depending on their momentum. So now that we know what waves and particles are, we can actually discuss wave and particle duality. Wave and particle duality is the concept that every particle can be partially described as a wave. But how did we come to this conclusion? In the late 1800s, light was thought of as just waves, and matter was thought to consist only of particles. In 1900, Max Planck first proposed that light is emitted in quanta of energy. To put in other terms, he proposed there was some fundamental unit which made up light. In 1905, Albert Einstein published a paper which also theorized a fundamental unit, or particle, of light. A man by the name of Robert Millikan tested Einstein's theory, and in 1914 confirmed it. The test that Millikan used to prove Einstein's theory was known as the photoelectric effect. So here's how it works. A piece of metal is placed in a vacuum facing a conductive plate. This piece of metal begins charged with electrons on its surface. When a light with a high enough frequency, which correlates to energy, is shown on the metal, electrons are actually knocked off of the metal surface and make contact with the conductive plate. These electrons will now generate a current through the electric plate, which can be measured. Now, the only way electrons can be separated from this metal plate is through some sort of high-energy collision. Well, if light is merely a wave, it can't physically collide with the electrons. However, if light was made up of some sort of particle, then it would stand to reason if this light particle had enough energy, it could collide with the electrons on the plate and knock them off. And as you may know, these particles of light are what we call photons. We now have our first proven entity that acts as a wave and a particle. In 1924, a French physicist named Louis de Broglie hypothesized that not only does light have wave and particle characteristics, but so do all particles of matter. And this was proven in an experiment performed by Clinton Davison and Lester Germer. Their experiment consisted of firing an electron beam through a pinhole at a nickel chloride crystal. A sensor rotated around the crystal during this and detected a peak in intensity at various points. These peaks revealed an interference pattern, which is found only in waves, thus leading them to the conclusion that electrons have to act as waves. There's a modern experiment which is built on Thomas Young's slit experiment from 1801. This modern experiment is called the double slit experiment, which supports Davison and Germer's findings. So here's how the double slit experiment works. Let's say you have a board with two vertical slits in it side by side. Now let's say you were to fire marbles through the slits, with a screen behind them to catch the marbles. What do you think would happen? Intuitively, you would think that two separate vertical patterns would form on the screen. And you're right. That's how physics works. We know this. We've seen this scenario played out many times in many different ways. Now if you submerge the board in water, and this time sent waves through the slits, what do you think would happen? Well, the waves go through the slits, they disperse radially outward and interfere with each other. We can see that they will superimpose on each other. That is, if the peaks of two waves meet, the intensity at that point will be double. But if the peak of one wave meets the trough of another, it will cancel out the wave. We see when the wave hits the screen that there are points of high intensity separated by points of no intensity. This means there are points where no waves hit the screen. So this all makes pretty good sense. Essentially, we could have predicted these outcomes given a little knowledge of physics. So now let's look at this experiment using microscopic particles, such as electrons. If you just have one slit and you shoot electrons through it, just as before, you would see a scattered vertical line of electrons form on the screen. But the most bizarre thing happens when you fire electrons through both slits at once. We see the interference pattern that we did with the waves. How is this possible, though? We fired a particle, not a wave. Scientists thought that maybe after going through the slits, the particles collided and were dispersed. So they repeated the experiment, but fired one electron at a time in order to avoid any possible collisions. But to their surprise, the particles still exhibited this interference pattern. How was this possible? Were particles in the past interfering with particles in the future and vice versa? Or by some incredible means, was the particle starting as a particle, separating into a wave, going through both slits, interfering with itself, then going back together and hitting the screen? This was the only thing they could think of, but they wanted to get a closer look. So they decided to place a small device near the slits, which emits a light when it detects an electron. Surely by doing this, they'll be able to find out which slit the electrons are going through. Are they going through one, the other, both, neither? But it appears nothing can be so simple, because when they did this observation, the electrons began behaving like particles again, as in they produced two vertical lines on the screen. What does this mean? Simply by observing the electrons, they behave differently? If you think about it, it's such a big coincidence because we finally found a phenomenon which defies our known physics. But when we try to get a closer look to debunk it, the phenomenon stops. Do the electrons somehow know we're watching them? Is the universe aware? Does it not want us to find the answer? This is a good example of why we use quantum mechanics. It seems that physics works differently on such a small scale. This phenomenon, where simply viewing something changes the way it acts, is referred to as the observer effect. And there might be a few explanations for this observer effect taking place when viewing electrons. My personal theory is that the recording device used to observe the electrons has an electric current moving through it. Now, we know that electrical currents create magnetic fields. Perhaps this magnetic field that's being created from this observing device is somehow interacting and canceling out the wave function of the particle, causing them to behave as particles again. Now, some people like to say that this is proof that we're in a virtual reality, that this has to be the work of some computer programming, but I'm not too sure about that. I'll let you guys decide. Well, there you have it. That is wave and particle duality, the concept that waves and particles are intermingled, that particles exhibit wave and particle-like behavior. There's a lot that we still don't know about quantum mechanics, and a lot that we still don't know about particles. But hopefully in time we'll figure it out.